Imagine, just for a moment, that you are a military mechanic.
Right.
And you're stationed, a few miles behind the front lines of a major conflict. A heavily armored 700-kilogram ground robot rolls into your maintenance bay.
A beast of a machine.
Yeah, exactly. It basically looks like a miniature tank.
Yeah.
And it has a broken power cable. Now, in any normal war, you would just walk over to a shelf, grab a spare cable, plug it in, and send that machinery back out.
Sounds simple enough.
Right. But right now, you can't, because you currently have 550 different types of robots operating in your sector,
This is wild.
built by 270 different companies. None of their parts match. The software interfaces, they don't communicate. So that $100,000 piece of life-saving machinery is now just a very heavy, very expensive paperweight.
It is the ultimate technological nightmare. I mean, you have all this incredible innovation happening at breakneck speed, but without standardization, you essentially just build a massive, unmaintainable junk pile.
And that logistical chaos is exactly what we are unpacking today. We have a massive stack of intelligence reports, engineering specs, defense analyses, and, real-world operational data detailing the reality of the war in Ukraine.
Right, there's a lot of material here.
There is. And our mission for this deep dive into the sources is to understand the future of unmanned systems, specifically how militaries are desperately trying to solve that Tower of Babel problem.
Right, getting all on the same page.
Exactly. How unmanned aerial vehicles, UAVs, and unmanned ground vehicles, UGVs, are being forced to integrate into a single, cohesive, almost telepathic fighting force. And just a quick note before we jump in.
Go ahead.
We are looking strictly at the technological realities and engineering data detailed in these texts. We're impartially reporting on how these systems are evolving under extreme conditions, without taking any political sides.
Absolutely. And just to give you a roadmap of where we're heading on this journey today, first we need to understand the new reality on the ground. It's a concept called the metal goes first doctrine.
Metal goes first. Got it.
Right. And we'll look at why this massive robotic workforce shift is happening in the first place. Second, we'll dive deep into the universal language these machines are adopting to actually talk to each other.
Which is fascinating.
It really is. It's a standardized protocol known as DroneCAN. Third, we will examine how humans fit into this loop through manned-unmanned teaming, or MUMT, and how they build these resilient three-dimensional combat networks.
Okay.
And finally, we'll look at the sheer mind-bending speed of modern agile development, where lethal hardware is being tested, simulated, and updated in just a matter of weeks.
I want to start right there with this metal goes first doctrine, because,
Mhm.
I mean, if I buy a laptop today, I expect it to connect to my home Wi-Fi flawlessly.
Right.
If I buy a smart light bulb, I expect to talk to my phone. So why was coordinating a ground robot and a flying drone such a monumental disaster early on in this conflict? Like, before we get to the fix, help me understand the environment that created this mess.
Well, the environment that created this mess is, frankly, an environment of sheer desperation and catastrophic attrition.
Wow.
Yeah. The texts we're looking at, they paint a really vivid picture of modern high-threat combat zones. We're talking about dense urban warfare and brutal trench combat. In previous eras, the doctrine was to, lay down artillery fire and then send human infantry forward to secure the ground.
The old school way.
Exactly. But the human cost of that initial contact has just become entirely unsustainable.
Because the enemy has drones, too. I mean, every square inch of the battlefield is under observation.
Precisely. Well, it actually goes beyond just observation. It's instant lethal reaction.
Okay.
If a human steps out of a trench, they're spotted by a thermal camera on a drone, and artillery is falling on their position within 2 minutes.
Few minutes, that's terrifying.
It is. So the tactical goal has explicitly shifted to reducing human casualties to absolute zero during the initial phases of an engagement. You have to offload the physical risk. You're trading disposable machines for irreplaceable manpower.
And that leads to the rapid prototyping, right? And the 270 different manufacturers just jumping into the fray to build something, anything.
Right. Everyone wanted to solve the problem.
Every startup, every engineering university, heavy machinery companies, they all started building ground robots to fill that desperate need. Which brings us to the hardware itself. The reports highlight some unbelievable pieces of machinery making this doctrine a reality.
Oh, definitely.
The one that absolutely blew my mind is a Ukrainian platform called the Armalab Mamont, which translates to mammoth. And if you listening are picturing a little remote-controlled car or like a bomb disposal robot with tank treads, you need to wipe that from your mind.
Yeah, the scale is entirely different here. The Mamont is a beast. It's an unmanned ground vehicle that can autonomously carry a 700-kilogram payload.
700 kilos.
Yes, and it has an operational range of 100 kilometers across contested, highly dangerous territory.
Let's just put 700 kilograms into perspective for a second. That is roughly 1,500 pounds. That is the weight of an entire adult grizzly bear.
Or a classic Volkswagen Beetle.
Exactly, just in payload capacity. How does that fundamentally alter frontline logistics?
It changes everything. I mean, think about how a trench position is normally supplied. Humans have to carry heavy boxes of ammunition, water, winter gear on their backs, hiking through miles of mud.
Under constant threat of sniper fire and artillery.
Right. It's exhausting, it's slow, and it's deadly. The Mamont takes that entire logistical burden off their shoulders. It hauls vast amounts of heavy artillery shells, heavy machine gun ammunition, and critical supplies directly to the zero line.
That's huge.
But the texts emphasize that its most vital role isn't just bringing things in, it's actually bringing people out.
The medevac missions, the combat casualty care.
Yes. Imagine a scenario where a soldier takes shrapnel to the leg in a forward trench. They're bleeding heavily. In the past, you'd have to send a human medical team of at least 2, maybe 4 people, carrying a stretcher, running under active enemy fire to retrieve that one wounded soldier.
Right, you're risking 4 healthy lives to save 1 injured life.
It's a terrible mathematical calculation that combat medics have to make every single day.
But with the Mamont.
With the Mamont, the human medics stay in a reinforced bunker 3 miles back. The UGV autonomously navigates to the GPS coordinates of the trench. The infantrymen in the trench load their wounded squad mate onto the Mamont.
Wow.
And then the vehicle actually lowers specialized armored plates to shield the casualty, and it drives itself back to the medical checkpoint.
That's incredible.
It's performing a task that has a near 100% chance of drawing enemy fire. But the only thing that might get destroyed is metal and code.
That is profound. It really crystallizes the metal goes first ethos. But, you know, as I read through the engineering specs, a glaring limitation jumped out at me. These ground robots, as tough and powerful as they are completely bound by physics and terrain.
They are entirely earthbound, yes. And the earth in a war zone is arguably the most hostile terrain imaginable.
Right. We're talking about Rasputitsa, that deep freezing mud that just swallows vehicles whole. We're talking about anti-tank ditches, concrete dragon's teeth, dense forests shattered by artillery.
In minefields, incredibly dense minefield.
Exactly. The Mamont might be able to haul a literal ton of gear, but if it encounters a flooded 5-meter-wide artillery crater or a wall of collapsed urban debris, it just stops. It becomes a 1,500-pound roadblock.
Which is exactly why the standalone ground robot is an evolutionary dead end.
Oh, really?
Yeah. The texts make it clear that the future relies entirely on symbiosis. The air and the ground have to work together. This is where the aerial drones, the UAVs, enter the equation to compensate for the UGV's physical limitations.
Okay, so how does that work in practice? Like if I'm a soldier waiting for my 700 kilos of ammo and the Mamont is stuck behind a crater half a mile away, how does a drone fix that?
Through what the logistical reports call a last-mile bypass mechanism. So heavy-lift multi-rotor drones, think large octocopters, are integrated into the same unit. If the Mamont gets bogged down by impassable terrain or reaches a minefield that's just too dense, it stops in a secure location. The heavy-lift drone then flies out from the rear, rendezvous with the UGV, physically lands on it or hovers just above it.
And picks up the cargo.
Exactly.
Yeah.
It picks up the most critical supplies, say the medical kits and the mortar, fuses, hops over the impassable crater, and drops the payload directly into your trench.
It's like a hybrid delivery service. The truck takes it 99% of the way, and the delivery drone takes it up the stairs to your apartment.
Right.
Except the apartment is a trench and the stairs are an active minefield.
That is an excellent analogy.
Okay.
And importantly, the symbiosis works in reverse as well. Ground vehicles are heavy, but they have massive batteries or diesel generators.
Lots of power.
Lots of power. Aerial drones are fast and they bypass terrain, but they are severely constrained by battery life and payload weight. A small reconnaissance drone might only be able to fly for 25 minutes before its battery dies.
Which isn't a lot of time if you're trying to maintain a persistent eye on an enemy position.
Not at all. So the UGV acts as a mobile aircraft carrier and charging station.
Oh, that's smart.
Yeah, the drone flies its 20-minute mission, locates an enemy bunker, and instead of flying all the way back to the human operator miles away, it lands directly on the Mamont.
And charges right there on the front line.
Exactly. The Mammoth recharges the drone's batteries, and 5 minutes later, the drone is back in the air. This extends the operational time of the aerial asset from minutes to hours or even days.
And the texts also describe them working together offensively, right? Like the UGV can act as the heavy muscle-carrying and automatic grenade launcher or a .50 caliber machine gun, while a tiny, practically invisible quadcopter hovers 300 feet above it, acting as the spotter.
The drone acts as the elevated optic nerve for the ground vehicle.
Yep.
It feeds targeting coordinates down to the UGV, allowing the ground robot to fire over hills or around buildings without ever exposing its own cameras to enemy fire.
Okay, I love this on paper. It sounds like a beautifully choreographed, high-stakes automated warehouse. But here is my major point of pushback, and this brings us back to my very first question.
Let's hear it.
Having a flying drone and a massive ground robot share data sounds incredibly futuristic. But we just established that early in this conflict, there were over 550 different types of UGVs built by 270 different companies.
Right, the Tower of Babel.
Exactly. If the aerial drone is built by a small software startup in Kyiv and the Maman is built by a heavy machinery company, how on earth are they actually communicating?
It's a huge problem.
I mean, we all know how frustrating it is when an Apple device refuses to talk to a Windows device, or when an app updates and suddenly your Bluetooth headphones stop working. How are these machines exchanging complex targeting coordinates in real time while people are actively shooting at them?
That was the multi-million-dollar bottleneck, and the reality on the ground was exactly as you described it, total logistical and operational paralysis. Yeah. If a military unit received 3 different UGVs from 3 different manufacturers, they essentially had to operate 3 completely isolated technology ecosystems.
A mechanic's worst nightmare.
A mechanic's nightmare, a trainer's nightmare, and a commander's nightmare. The spare parts didn't match, the control pads were different, the telemetry data was encrypted in proprietary formats.
So they couldn't even share controllers?
No. If a unit-specific UGV controller got crushed under a tank tread, they couldn't just use a controller from a different brand. The entire UGV was useless. You cannot execute a highly coordinated multi-domain robotic war if your robots literally cannot speak to one another.
So the industry had a massive forcing function. They desperately needed a universal translator. And by diving into the engineering specs, it is clear that they found one.
They did.
This brings us to a protocol that's mentioned on almost every page of these technical documents. DroneCAN, along with its associated architecture, CIFL.
DroneCAN is the gold standard that is rapidly unifying this fragmented industry.
I want to spend some serious time here and do a deep technical dive, because for you listening, if you want to understand how modern hardware actually works, not just in warfare, but in robotics, in aerospace, in autonomous cars, you have to understand how the internal nervous system is wired.
It's foundational.
So how does DroneCAN actually work to unite these 550 different robots? Let's start at the physical layer, the actual wires.
To understand DroneCAN, we have to go back in time a little bit. It's built on a physical communication layer called the CAN bus, which stands for Controller Area Network. Now, CAN bus is not a new experimental military technology. It was developed by Bosch in the 1980s for the automotive industry.
Wait, so it's in our cars right now?
It is in every modern car on the road. Think about how a car used to be wired in the 1970s.
Okay.
If you wanted a switch on your driver's side door to roll down the passenger side window, you had to run a thick, heavy copper wire all the way from that switch through the dashboard across the car and into the passenger door motor.
That sounds heavy.
It was. As cars got more complex, anti-lock brakes, fuel injection, climate control, the wiring harnesses became massive, heavy, and incredibly complex.
So Bosch invented a network instead of a direct wire.
Exactly. CAN bus is a central simplified nervous system. Now, when you press that window switch, the switch doesn't send physical power to the motor. It sends a digital message over the shared CAN bus network.
So it's just sending data.
Right. The message essentially says, I am the driver's window switch, and my state is now down. The motor in the passenger door is listening to the network, hears that specific message, and activates itself. It reduced the wiring weight in cars by hundreds of pounds.
And DroneCAN takes that battle-tested, incredibly robust automotive layer and scales it for high-performance aerospace and robotics. The text specifically mentioned they're using something called CAN-FD. What is the FD?
Flexible data rate. Traditional CAN bus is highly reliable but relatively slow because it was designed for simple car commands. CAN-FD allows the network to push data rates up to 8 megabits per second.
Okay, so a lot faster.
Much faster. That means it can handle much larger, more complex data payloads like high-resolution telemetry, battery cell diagnostics, or rapid gyroscope updates, which are essential for a flying drone trying to balance itself in high winds.
Okay, that makes sense for the bandwidth. But if I'm building a drone in 2026, why use wires at all? Why not just use internal Wi-Fi or Ethernet or USB like my computer does? Why is CAN bus so uniquely suited for a war zone?
Because a war zone is not a quiet office. It is an environment absolutely saturated with military-grade electromagnetic interference, or EMI. Jammers are blasting radio frequencies at massive power levels to trap and scramble electronics.
So how does a wire defend against a radio jammer?
Through the genius of differential signaling. This is critical to understand. A CAN bus does not use one wire to send a signal. It uses two twisted wires. Let's call them CAN high and CAN low.
Two wires, okay.
When a microchip wants to send a digital 1, it sends a positive voltage down CAN high and an equal but opposite negative voltage down CAN low.
So it's sending the signal and the mirror image of the signal at the exact same time.
Exactly. Now imagine an enemy jammer hits the drone with a massive blast of electromagnetic noise. That noise creates a random voltage spike in the wires. But because the two CAN wires are twisted tightly together, the noise hits both wires equally.
Right.
If the jammer adds plus 5 volts of noise to CAN high, it also adds plus 5 volts of noise to CAN low.
Oh, I see where this is going. It's math.
It's simple, brilliant math. The receiving chip at the other end doesn't just read the voltage. It mathematically subtracts the value of CAN low from CAN high. Because the noise spike is identical on both wires, when you subtract them, the noise completely cancels out to zero.
That's amazing.
The only thing left is the pure, original digital signal.
It's exactly how noise-canceling headphones work, but for data. It is physically hardened against electronic warfare. And the texts also mention these 120-ohm terminal resistors at the ends of the CAN bus. What are those doing?
That's another physical safeguard.
Right.
When you send electrical signals down a wire at high speeds, when the signal hits the end of the wire, it can actually bounce back.
Like an echo.
Exactly like an echo. Like a ripple in a bathtub hitting the wall and reflecting back. That reflection scrambles the incoming data. The 120-ohm resistors act like shock absorbers at the end of the network. They absorb the electrical energy so it doesn't reflect, ensuring the data stream stays perfectly clean.
Okay, so the physical wires are practically indestructible against noise. But what about the software? How does a motor built by Company A actually understand the commands from a flight controller built by Company B? If the physical wires are the highway, what are the traffic laws?
This is where DroneCAN's software architecture is revolutionary. It operates on a stateless publish-subscribe model.
Stateless, publish, subscribe.
Right. And to understand why this is so important, you have to understand the legacy systems it replaced, which were built on a master-slave hierarchy.
A master-slave hierarchy, let me guess. There's one big computer in charge and everything else is dumb.
Correct. In older drones, the central flight controller was the master. Every other component, the GPS, the electronic speed controllers on the motors, the battery manager, were the slaves. The slaves were not allowed to speak unless the master directly interrogated them. The master would say, GPS, where are we? The GPS would answer. Then the master would say, Motor 1, what is your RPM? Motor 1 would answer.
It's like a boss micromanaging employees by calling them directly on the phone one at a time.
Yes.
But what happens if the boss's phone dies? Or what happens if a piece of shrapnel hits the main flight controller, or a power surge causes it to momentarily reboot?
In a master-slave system, the drone falls out of the sky.
Really? Just from a momentary reboot?
Yes, it's a massive single point of failure. If the master reboots, it has to wake up, reinitialize the network, perform a handshake with every single slave node one by one, and verify their status before it can issue a command. In drone flight dynamics, a delay of 50 milliseconds means you lose stability and crash.
So how does DroneCAN's publish-subscribe model fix that?
It entirely eliminates the master. It creates a decentralized peer-to-peer network. If the master-slave model is a private phone call, the publish-subscribe model is like a public radio broadcast.
Ah.
Every node on the drone simply publishes its data to the shared network at a set frequency, regardless of who is listening.
So the GPS is just constantly shouting, here are my coordinates, and the battery is shouting, I am at 80%, I am at 80%.
Exactly. They broadcast their messages with specific ID tags. Any other node on the network that needs that information simply subscribes to that tag and listens to the broadcast. The flight controller listens to the GPS broadcast to navigate and listens to the battery broadcast to calculate flight time left.
This sounds incredibly resilient. Let's run that catastrophic failure scenario again. The drone is flying. A missile explodes nearby. The electromagnetic pulse is so strong that the main flight controller actually crashes and has to reboot. What happens?
Under the DroneCAN publish-subscribe architecture, the subordinate nodes don't wait for a master. The motors keep spinning at their last known command.
Because nobody told them to stop.
Right. The GPS keeps broadcasting. The sensors keep gathering data. When the flight controller finishes its reboot, which the text state can happen in under 10 milliseconds, it doesn't have to perform a complex handshake with every component.
Just wakes up and listens.
It just tunes back into the radio station. It instantly starts receiving the published data, dynamic node allocation assigns it an ID, and it resumes control of the drone flawlessly. The physical vehicle barely twitches. It is the absolute definition of distributed, decentralized resilience.
And beyond surviving explosions, this publish-subscribe model completely solves the 270 manufacturers problem, right? It enables actual, true plug-and-play capability.
Yes, it is the holy grail of hardware integration.
The technical reports use the Lightware LiDAR as a prime example of this, and it's a fascinating case study. For context, Lightware makes these incredibly precise laser rangefinders. They bounce a laser off the ground to tell the drone exactly how high it is, down to the millimeter.
Which is crucial for smooth, autonomous landings.
Right. And in the old days, like 5 years ago, if an engineer wanted to add a new sensor like that to a custom drone, it was a nightmare.
It would take weeks of software engineering. They'd have to write custom drivers, splice wires, figure out the proprietary serial communication protocols, and recompile the entire flight control software from scratch just to test it.
But with their new DroneCAN adapter, the process is almost comically simple. The engineer takes the laser rangefinder, mounts it to the drone, and plugs a single 4-pin connector into the CAN bus network. That's it.
That is literally it. As soon as it receives power, the LiDAR sensor boots up and says, "Hello, network. I am an unassigned sensor. I need a node ID." The DroneCAN dynamic allocator instantly assigns it a unique number, say node 42.
Okay.
The sensor then starts publishing its laser distance measurements using the standardized DroneCAN message format.
And the flight controller, regardless of who manufactured it, sees the message, recognizes the standardized format for distance sensor, and immediately starts using that data to adjust its altitude. You can upgrade a military drone in a trench with a brand new sensor in 5 minutes with zero coding required.
That plug-and-play interoperability means that a commander can take a battery from manufacturer A, plug it into a motor from manufacturer B, control it with a computer from manufacturer C, and it all functions as a single unified organism.
But what blew my mind in these sources is that DroneCAN isn't just for the internal organs of a single drone, it scales up. Because it uses something called DSDL, this standardized language allows for cross-domain data sharing between completely different vehicles.
DSDL stands for Data Structure Description Language. It is a strictly defined, universal dictionary for data.
Okay, so everyone is speaking the exact same dialect.
Exactly. It means that an obstacle waypoint message looks mathematically identical, whether it's generated by a flying quadcopter or a 700-kilo ground vehicle.
Let's tie this back to our Mamont UGV and the aerial drone team we talked about in Section 1. How does DSDL actually make them work together in real time?
Let's paint a picture. The Mamont is driving through a ruined city street. It has a heavy radar unit bolted to its chassis. As it drives, the radar generates a complex 3D point cloud of the obstacles ahead: rubble, burned-out cars, enemy barricades.
Lots of raw data.
Yes. It translates that raw radar data into a standardized DSDL format and publishes it.
And because the UAV hovering 500 feet above the street also speaks DSDL.
The UAV subscribes to the Mamont's broadcast. The flying drone's flight controller can instantly parse the ground radar's point cloud. The flying drone can literally see through the eyes of the ground robot in real time.
That is staggering. It eliminates the translation lag. In older systems, the ground robot would have to send the data to a human operator. The human operator would have to look at a screen, identify the threat, type in coordinates, and send a new command to the flying drone.
Exactly. You're removing the human bottleneck for data processing.
Yeah.
It drastically reduces the latency between sensing a target and acting on it.
Wow.
The UGV sees a threat, publishes the coordinates in DSDL, and the UAV subscribes to that data and automatically swivels its camera to lock onto the target in milliseconds. There's no custom translation software needed in the middle.
Mhm.
The entire swarm of varied robots shares a unified, decentralized nervous system.
Which is simultaneously brilliant and terrifying. If you're listening to this, you might be having the exact same thought I had when reading these specs. We have essentially created a telepathic swarm of heavy machinery. They're sharing radar data, they're operating at millisecond latency, they don't need a central master computer to function.
It sounds like science fiction.
It really does. So where is the human leash? We aren't just letting 700-kilo autonomous killbots run wild across the countryside, right? How do humans actually command this complex system safely?
That is the critical question of modern doctrine, and it leads us directly into our third section, manned-unmanned teaming, or MUMT. MUMT is the operational architecture designed to keep the human firmly in command, but importantly, to keep their fragile physical body out of the line of fire.
The texts frequently use an analogy here that I find really helpful. They describe the human no longer as a foot soldier holding a rifle, or even as a pilot holding a joystick, but as the conductor of an orchestra.
It is a perfect metaphor. Think about how an orchestra works. The conductor stands at the podium. They don't actually play the violin. They don't blow into the trumpet.
Right.
They hold a baton, and they dictate the tempo, the volume, and the overall emotional direction of the piece. The individual musicians, highly trained professionals, figure out exactly where to put their fingers on the strings to execute the conductor's vision.
So in this scenario, the human is the conductor, and the various autonomous UAVs and UGVs are the musicians.
Precisely. And what makes this modern architecture so revolutionary is the length of the conductor's baton. The podium can be located hundreds of kilometers away from the actual instrument.
The human commander isn't sitting in a trench with a remote control anymore.
No. They might be sitting in a heavily fortified underground rear command post. Or they might be flying in a manned jet high above the battle space, entirely out of range of enemy air defenses.
That makes sense.
The texts highlight some fascinating concrete trials that prove this concept works. We're not just talking about theory. They detail exercises from the European FCAS program, the Future Combat Air System.
Specifically the Spanish trials, right. Walk me through what actually happened in the cockpit during those tests.
So in the Spanish trials, they successfully integrated fully autonomous UAVs with manned jet fighters. A human pilot is flying a high-performance jet. On their multifunction display in the cockpit, they don't have a joystick to fly the drones.
They just have a screen.
They have a tactical map. The pilot touches a location on the screen and selects a broad tactical command like reconnoiter this ridgeline or suppress that enemy air defense system.
That is the conductor waving the baton.
Exactly. The human dictates the what and the where. The autonomous edge nodes, the drones figure out the how.
Oh.
The drones communicate with each other using that DroneCAN and DSDL language we just discussed. They analyze their own battery levels, they assess the wind conditions, and they dynamically allocate the task among themselves. One drone might fly low to draw radar attention, while another circles high with an optical camera.
Without the pilot doing anything else.
They execute all the micro movements required to achieve the commander's goal without the pilot ever having to fly them manually. The trials even had rotary wing UAVs seamlessly coordinating with manned transport helicopters from the Spanish Army, scouting landing zones ahead of the human crew.
It is a masterclass in delegation. But how are they physically building this three-dimensional communication network? Because the conductor needs to send the sheet music to the musicians, and they are spread out over miles of contested terrain.
It requires a layered network.
Right. The engineering reports detail a highly layered approach, and it almost always starts with an eye in the sky. They extensively feature a platform called the Raybird 3.
The Raybird is a fascinating piece of engineering that acts as the central router for this 3D network. It's a high-altitude, long-endurance drone. It has a wingspan of almost 3 meters, but because of advanced composite materials, the entire aircraft weighs less than 25 kilos.
It's essentially a flying radio tower, but what caught my eye in the specs isn't just its size, it's the propulsion system. The latest iterations of the Raybird are moving away from traditional internal combustion engines and batteries and moving toward hydrogen fuel cells.
Yes, hydrogen is the future for these platforms.
But why hydrogen? If I'm building a drone, why not just put a lawnmower engine in it or a bunch of lithium-ion batteries?
It comes down to 2 critical factors, stealth and endurance. Let's tackle stealth first. Internal combustion engines, like a lawnmower engine, rely on friction and tiny explosions. They are incredibly loud.
True.
But more importantly, they generate a massive amount of heat. As the texts point out, an exhaust pipe glowing at 400 degrees in the infrared spectrum is essentially a neon billboard for modern anti-aircraft thermal sensors. It screams, "Shoot here!"
And batteries, they're quiet, right?
Batteries are quiet, but they are heavy, and they lack the energy density for multi-day endurance missions. Hydrogen fuel cells offer the holy grail. They produce electricity chemically by combining hydrogen and oxygen across a proton exchange membrane.
So what's the exhaust?
The only byproducts are electricity and water vapor.
So there are no moving pistons?
No pistons, no explosions. They're acoustically near silent. And crucially, their thermal signature is incredibly low. A hydrogen-powered Raybird can loiter at high altitudes for 24 hours, practically invisible to infrared tracking, acting as the ultimate undetectable conductor's baton high above the battlefield.
Okay, so we have this silent, invisible router in the sky. How does it pass the massive amounts of data down to the players on the ground? Because DroneCAN is great for the internal wiring of a robot, but it isn't designed to beam 4K video across 10 miles of airspace.
Correct. For the external long-range data links, the network relies on high-bandwidth protocols. Specifically, one mentioned heavily in the text called Micro XRC EDDS.
That's quite an acronym.
It is. This is usually paired with 5G cellular technology or encrypted software-defined radio SDR mesh networks.
Okay, let's break down that acronym soup. Micro XRC EDDS. What is it actually doing?
It stands for Extremely Resource-Constrained Environments Data Distribution Service. Think of it as an ultra-efficient bridge. It takes the highly structured, critical data from the drone's internal flight controller and securely bridges it directly to advanced companion computers that are running ROS2, the robot operating system.
Why is that bridge necessary?
Because flight controllers are built for stability, not heavy data processing. ROS2 allows the system to handle massive, heavy data streams like live, high-resolution optical video feeds, thermal imaging, or dense radar telemetry, and transmit them across the network with incredibly low latency.
So the Raybird is up there, silent and invisible, gathering this high-resolution targeting data through its cameras. In the old paradigm, it would beam all that heavy video data all the way back to a command post. A human analyst would stare at a monitor, spot a tank, type the coordinates into a different computer, and then send those coordinates out to a weapon system.
Which takes minutes. In modern combat, if you take 2 minutes to strike, the target has already moved.
So how does the MUMT 3D network change that?
It skips the middleman.
Yeah.
The human conductor sets the rules of engagement, but the network handles the routing. Using that micro XRC EDDS and the SDR mesh network, the Raybird processes the target and beams the high-resolution data directly to the edge nodes.
The musicians.
Exactly.
Yeah.
For example, it beams the exact coordinates directly to a ground-based Mammoth UGV hiding in a tree line, equipped with a Shabliya K2 remote weapon station.
Okay.
The Shabliya features automated targeting algorithms and heavy machine guns. Simultaneously, the Raybird beams that exact same target data to a swarm of Lancet 3 loitering munitions kamikaze drones that are circling 10 miles away.
It allows the commander to orchestrate a three-dimensional saturation strike. The human authorizes the engagement, and the silent drone in the sky feeds the coordinates to the ground robots and the aerial missiles simultaneously. They attack the target from multiple vectors at the exact same second.
Yes.
And the human commander is sitting safely in a bunker 50 miles away.
It expands the lethal reach and situational awareness of a single human being to an unprecedented scale without exposing them to physical danger.
But, and this is a massive but, if you're listening to this, you have probably spotted the critical vulnerability in this entire beautiful symphony. We have turned the human into an orchestra conductor. The network is singing across hydrogen drones and ground robots. But what happens when the enemy realizes this and turns on a massive electronic warfare jammer?
The million-dollar question.
Right. What happens when they flood the 5G and SDR radio waves with absolute static and the conductor's sheet music disappears? If the conductor can no longer talk to the musicians, doesn't the whole symphony crash into chaos?
That is the defining vulnerability of unmanned warfare. It is the exact problem that defense engineers are losing sleep over. The operational environment described in these intelligence reports from Ukraine is the most dense, sophisticated electronic warfare environment in human history.
Wow.
The airwaves are a war zone of their own. GPS signals are routinely spoofed, sending drones flying into the ground. Radio frequency command links are jammed with raw power. Telemetry data is severed.
So how do you maintain this elaborate 3D MUM-D network when the airwaves are literally full of garbage? How do the machines adapt?
The machines have to adapt physically, and they have to adapt algorithmically. Let's look at the physical adaptation first, because it is fascinating. When communication links start degrading due to jamming or terrain, the systems don't just blindly continue on their path and hope for the best.
What do they do?
The texts detail a cooperative control framework based on what they call dynamically varying modulation matrices.
Okay, I need an ELI 5 explain it. Like I'm 5 for modulation matrices. What does that actually look like in the physical world?
Let's go back to our UAV and UGV team. A flying drone is scouting ahead for a ground robot in a ruined city. They're communicating via radio waves. Suddenly, the ground robot turns down a street, and a massive, concrete, high-rise building comes between the robot and the flying drone.
Okay, blocking the signal.
Right. This creates a non-line of sight, or NLOS, condition. The concrete blocks the radio signal. The connection drops.
The sheet music is gone.
Exactly. In a dumb system, the vehicles would just lose connection, trigger a failsafe, and try to return home. Or they might try to just blast their radios at maximum power to punch through the concrete, which drains the battery and gives away their position to enemy sensors.
But with a modulation matrix.
The modulation matrix is constantly calculating the geometry of the physical environment and the physics of radio wave propagation. It mathematically maps the occlusion, risks the blind spots in real time based on the map data.
Okay.
When the signal starts to degrade, the matrix dynamically adjusts the velocity vectors, the physical speed and the physical flight path of both vehicles simultaneously.
Wait, they physically moved just to save the Wi-Fi connection.
Exactly. The UAV will autonomously alter its flight path, perhaps banking hard to the left to peek around the edge of the high-rise building. Simultaneously, the UGV on the ground will slow its treads or back up 10 feet to ensure that an invisible line of sight is restored between its antenna and the drone's antenna.
That is incredible.
They prioritize the integrity of the network over taking the most direct path to the target. They perform this intricate physical dance around obstacles to keep the connection to the conductor alive.
That is brilliant. They're treating the radio link as a physical tether that cannot be broken.
Oh.
But let's take it to the absolute extreme. What if they aren't just blocked by a building? What if the enemy jamming is so overwhelmingly powerful that even line-of-sight communication doesn't work?
Then you have a real problem.
What if the radio link to the human commander is totally irreparably severed?
Then the system crosses the Rubicon. It relies entirely on edge AI. The operational doctrine transitions from having the human on the loop to the machine being completely out of the loop. It becomes fully autonomous.
Okay, let's break down how that actually works, because if the GPS signal is jammed, my phone doesn't know if I'm in New York or Tokyo. How does a drone navigate a war zone without satellites?
It uses visual odometry. It navigates the exact same way human explorers used to navigate, by looking at the ground and looking at a map.
But how does a computer do that without a human eye?
Before the drone ever takes off, it is loaded with high-resolution satellite imagery of the entire operational area in its onboard memory. As it flies, its downward-facing optical cameras are recording a live video feed.
Okay.
The onboard computer, running advanced neural networks, constantly compares the live video pixels to the stored satellite map.
It's looking for landmarks.
Exactly. It uses feature extraction algorithms. It looks for the specific geometric curve of a river bend, the intersection of two major highways, or the distinct square outline of an industrial building. By mathematically correlating the live video geometry to the 2D map, it can calculate its exact longitude, latitude, and altitude without ever needing a single ping from a GPS satellite. It knows precisely where it is entirely on its own.
Okay, so it knows where it is, it hasn't crashed. But how does it actually execute a combat mission? How does it find and strike a target without the human conductor pointing at a screen and saying, attack that tank?
Through highly advanced automated target recognition processing happening right on the edge node. The drones are equipped with powerful onboard processors, like NVIDIA Jetson modules.
Okay.
These chips are running deep learning neural networks that have been trained on hundreds of thousands of images of military assets. They can recognize the shape of an artillery piece, a radar dish, or a tank in milliseconds.
But the enemy knows this. We've seen videos of forces putting metal cages over tanks or tying tree branches to vehicles to confuse the drones. And the sources mention a specific, very old-school counter-tactic that blew my mind. Painting armored vehicles with high-contrast, zebra-like black and white stripes.
Ugh, dazzle camouflage. It is a fascinating return to historical tactics. Militaries used dazzle camouflage on battleships during World War I to confuse human submarine commanders looking through periscopes.
Because it makes it hard to tell how fast the ship is moving or where the front of the hull is?
Exactly. And it turns out it works incredibly well against early AI computer vision models. The high contrast stripes break up the visual geometry of the vehicle.
So the AI gets confused?
Yes, a neural network trained to look for a big green rectangle gets confused by the chaotic black and white lines. The optical camera sees it, but the algorithm fails to classify it as a tank.
So how does the modern edge AI beat the zebra paint? If the radio is dead and the human can't step in to say, hey, dummy, that's obviously a tank, how does the drone figure it out?
By not relying on just one sense, the modern edge AI utilizes a dual validation mechanism. It looks at the world through two completely different spectrums simultaneously.
Okay, what are they?
It looks at the geometric shapes with its standard optical camera, but it also looks at the thermal signature with its infrared camera.
Ah, you can paint a tank to look like a zebra.
But you cannot hide the heat of a 1,500 horsepower diesel engine block.
The physics of thermodynamics won't let you hide.
Precisely. The visible light geometry might be entirely distorted by the dazzle paint and the tree branches. But the infrared camera sees a glowing, unmistakable thermal outline of the engine block, the exhaust manifold, and the friction heat on the tank treads.
And it puts it all together.
Right. The onboard AI fuses those two data streams. It realizes the optical data is corrupted, validates the target using the thermal data, locks onto the heat signature, ignores the camouflage entirely, and autonomously adjusts its terminal dive trajectory to strike the target.
It's chilling, really. The drone carries its own intelligence, its own autonomous navigation, and its own multi-spectrum targeting. When the electronic warfare severs the tether to the human conductor, the machine doesn't shut down. It becomes a closed-loop system that jamming simply cannot stop because it requires absolutely zero external signals to complete its mission.
It is the ultimate realization of the autonomous edge, and it is highly effective.
Which brings us to a massive overarching question. And this transitions us into our final section. The neural networks processing thermal data on the fly, the modulation matrices dynamically routing robots around buildings, the universal standard of DroneCAN.
It's a lot of tech.
It is incredibly sophisticated, bleeding-edge technology. How are militaries building and deploying these complex systems so fast? I mean, historically, if the military wants to build a new fighter jet or a new tank, it takes a decade or more of bureaucracy.
The historical model of defense procurement is dead. It has to be. The traditional cycle where a military spends 3 years writing a requirements document, another 5 years testing prototypes in sterile, perfect laboratory conditions, and then slowly fielding a system over a decade, it cannot survive in the modern era.
The enemy moves too fast.
Exactly. As one of the reports bluntly states, a system that works perfectly in a laboratory test but fails when exposed to real-world electronic jamming is operationally useless.
The enemy isn't going to wait 10 years for you to update your software. And the innovation we are seeing detailed in these reports isn't happening in 10 years. The texts say innovation is happening in software-like sprints of 2 to 8 weeks.
It is a profound industrial and cultural shift. The defense industry has essentially adopted the agile development model pioneered by Silicon Valley software companies, but they're applying it to lethal hardware.
I really want to walk the listener through this 2 to 8 week iteration loop because the sheer speed is staggering. The texts highlight Ukraine's Brave One defense accelerator as a prime example of this new paradigm. Let's create a timeline.
Okay, let's do it.
Imagine it's a Tuesday on the front line. A drone operator launches a reconnaissance mission. Suddenly, their drone just drops out of the sky. The enemy has deployed a brand new, never-before-seen electronic jamming frequency. In the old days, that would mean a whole fleet of drones is grounded for 6 months while a congressional committee studies the problem.
But under the agile model, there is a seamless, continuous, real-time feedback loop between the frontline operator in the trench and the rear echelon engineers in the lab. The telemetry data, the exact black box recording showing how, when, and on what frequency the drone failed, is immediately encrypted and sent back to a 247 engineering team.
So it's Wednesday morning. The engineers receive the data. They isolate the new jamming frequency. They immediately start tweaking the algorithms to filter it out. But what if the fix requires a physical change?
What do you mean?
Like, what if they realize the drone needs a slightly different antenna shape to bypass the jammer, or a new aerodynamic housing? They can't just tool up a massive factory line overnight.
They don't need to. They rely on decentralized rapid manufacturing. They use high-end 3D printing, specifically techniques like SLS, selective laser sintering, using carbon fiber reinforced nylon for extreme durability.
Wow, okay.
Or they use rapid CNC machining to churn out the new aluminum parts. They can iterate a physical aerodynamic or structural change, print a batch of 50, and test them in days rather than months.
And if it is a software fix, which it often is, they recompile the new code and prepare to push it to the entire fleet. But wait, here's where my mind hits a roadblock. How do they know the new code won't accidentally crash all their own drones? You can't just push an update like a buggy smartphone app and hope it works when lives are literally on the line.
That is the tightrope they have to walk, speed versus safety.
Yeah.
And that is where virtual crash testing comes in. The engineering specs detail two critical simulation phases, SITL and HITL. These are the tools that allow them to move this fast without breaking their own systems.
Okay, break those down for me. Let's look at SITL first, software in the loop. How does SITL work?
SITL is entirely virtual. The engineers take the mathematical physics model of the drone, its weight, its motor power, its aerodynamics, and they take the brand new software code they just wrote on Wednesday. They run that code inside a highly realistic virtual physics environment like Gazebo or ROS2.
So it's like a hyper-realistic video game for the drone code.
Exactly. But they don't just fly it once to see if it works. They run massive Monte Carlo simulations. They use server farms to run tens of thousands of virtual flights simultaneously.
All at once?
Yes. They subject the virtual drone to varying wind shears, varying payload weights, and they simulate the exact new enemy jamming frequencies. If the software crashes in the matrix, they tweak it and run 10,000 more flights.
Okay, so the software proves it works perfectly in the virtual world. But as anyone who works in tech knows, software often behaves very differently when it hits actual physical silicon chips.
Which brings us to the most crucial step, HITL, or hardware in the loop. This is where it gets really interesting. Once the software passes the SITL tests, they take the actual physical brain of the drone, say a Pixhawk flight controller circuit board, and they sit it on a desk in the lab.
Just the board?
Just the board. They load the new experimental software directly onto that physical board.
So the board isn't attached to a real drone, it's literally just sitting on a desk.
Right. Then they take cables and connect the input and output pins of that physical circuit board directly back into the simulator computer.
Oh, wow. So the physical brain of the drone thinks it is actually flying.
Exactly. The simulator computer feeds the Pixhawk fake sensor data in real time. It feeds it fake GPS coordinates, fake gyroscope tilts, fake wind resistance. The Pixhawk processes that data using its physical microchips, calculates the necessary adjustments, and sends back physical electrical commands that are supposed to go to the motors.
And the simulator reads it.
The simulator reads those motor commands and updates the virtual physics accordingly.
It's basically putting the flight controller into the matrix. Why go through all that trouble, though?
Because it allows the engineers to test the real-world processing limits and thermal limits of the physical microchips. The simulator can throw data at the board faster than the processor can handle just to see how it fails. More importantly, they can inject catastrophic high-intensity faults safely on a desk.
Give me an example of a catastrophic fault test.
Imagine the HITL simulation is running. The virtual drone is flying at 100 meters, carrying a heavy 5-kilo payload. The engineers sit at their keyboards, and at the exact same millisecond, they tell the simulator to inject two catastrophic events.
Okay.
First, they simulate a massive GPS spoofing attack, telling the Pixhawk it is suddenly at the bottom of the ocean. Second, they simulate a power failure on motor number 3, dropping its RPM to 0.
So they intentionally break it to see how the new code reacts.
They sit back and watch the data cascade. Does the new firmware instantly switch to visual odometry when the GPS fails? Does it dynamically increase power to the remaining 3 motors to stop the drone from going into an uncontrollable spin?
Does it recover?
Right. Does it safely auto-land, or does the processor get overwhelmed and freeze? They push the physical hardware and the new software to its absolute breaking point on the bench, over and over, before a single physical drone ever leaves the ground.
And once it passes that brutal HITL testing,
It is certified for deployment. Within that 2 to 8 week window, an OTA over-the-air firmware update is beamed securely via encrypted channels to every drone in the fleet, whether they are sitting in a warehouse or active in a trench.
and the physical parts?
If the fix was physical, the new 3D printed modular parts are loaded onto supply trucks, or UGVs, and shipped to the front. By the time the enemy thinks they have developed a solid countermeasure and trains their troops to use it, the drones have already evolved to bypass it entirely.
So if we take a step back and look at this entire ecosystem, the defense industry has basically adopted the Silicon Valley move fast and break things model, but they are doing it in an environment where the stakes are literally life and death. The battlefield itself has become a giant real-time research and development laboratory.
It is digital Darwinism in its absolute purest form. If a system, whether that is a robot, a software protocol, or a military bureaucracy, cannot adapt its software, swap its frequencies, or physically reroute its path around obstacles in a matter of weeks, it goes extinct on the modern battlefield.
Okay, let's try to pull all of these threads together. For you listening, whether you are prepping for a tech meeting, studying logistics, or just intensely curious about the future, why does all of this matter?
It's the big so what.
Right. The core takeaway here is that this isn't just a grim military history lesson. This deep dive is a masterclass in modern systems engineering, the absolute necessity of standardizations, and extreme organizational adaptability.
Absolutely. If there is one thing to take away from these sources, it is that the future of unmanned operations, and really the future of automation in any sector, isn't about building a single, highly advanced, incredibly expensive, perfect machine.
The perfect drone.
Right, the exquisite multi-million-dollar drone is too fragile. The future is about building a resilient, interconnected system. It is about a disposable robotic workforce taking the physical risks, bound together by the standard decentralized language of DroneCAN, which prevents any single point of failure from bringing down the network.
It's orchestrated by human conductors through MUMT 3D networks. It keeps the flesh and blood decision makers entirely out of the line of fire while saturating the airspace and the ground with coordinated, highly lethal machines that can share radar and thermal data instantly.
And perhaps most importantly, it is a system that is constantly evolving through breakneck agile development and simulated crash testing. It proves that in any complex, highly contested environment, whether that is a literal battlefield, a highly volatile economic market, or a rapidly shifting technology sector, the speed of your iteration cycle, the standardization of your communication protocols, and your ability to ruthlessly remove human bottlenecks from data processing are the ultimate keys to survival.
You know, we started this journey by asking you to imagine a battlefield where metal and code take the hit instead of human beings. A scenario where the mechanic can actually fix the robot because the parts finally match. But after seeing how fast these systems learn, after breaking down how they navigate using visual odometry when satellites die, how they use fused thermal imaging to bypass camouflage, and how they rewrite their own software to defeat electronic jamming in a matter of weeks, it leaves you wondering where this is ultimately headed.
It raises a profound and somewhat unsettling question. We have intentionally designed a multi-domain robotic system that can perceive its environment with superhuman clarity, share complex data across standardized networks in milliseconds, and allow its own software to be rewritten based on changing conditions faster than any traditional human bureaucracy can track. We built them to survive without us. If the machines are adapting this quickly, sharing data this flawlessly, and operating this autonomously at the very edge of the battlefield, at what point does the human conductor stop being the mastermind of the symphony and start becoming the slowest, most vulnerable node in the entire network?